Hello, Leah.
Hello, Jordan.
How are you?
Good, and you?
Pretty good. A little tired, but that's normal.
Oh, okay. Uh, how many credit hours do you take this semester?
I have 5 research credit hours, and then somebody just knocked on my door.
Okay.
It's a UPS guy bringing my wife something from Target. I have 5 research credit hours and then 3 credits in this course, obviously.
Ah, yeah.
Wait,
Yeah.
or 6 credits. I can't remember. Maybe I have 6 credits. I
Yeah.
think I have 9 credit hours.
Okay. Yeah, but you just taken this course this semester. Just
Yeah.
you finished quantum.
I have Quantum 2 that I have to
Ah.
take. I already took the first one. So the first one is the one that's offered this semester, and then I'll take the second part of the course in the fall. And then I think that's the last actual course that I have to take.
Yeah.
Um,
Yeah, I think
yeah.
so. Yeah. Okay. We haven't taken the midterm exam in quantum. Maybe probably after the midterm.
Yeah. I think it gets all a bit confusing in that class when you take
I'm
exams and
already
homework.
confused.
Yeah, it's hard to keep up because you're not really sure what you're supposed to do.
Yeah.
There's not a lot of homework and stuff.
Yeah. So
There's a
let's not,
benefit to both, I think.
let's not begin with this because it might take some time to fix it and it may not be very productive as far as I can see. Can we talk about it later? Yeah. Right after this, there is a talk. After that maybe. Yeah. Can it do? When is this due? It's due today.
You actually put in the Eastville Thursday or next week.
Yeah, because I thought I won't be able to finish whatever I'm teaching is in a sense needed for the homework side.
So I just have all I have left is that little. I read through the article a couple of times and referenced it in my problem.
Which article is this? Oh, I see. Yeah.
All it said in part C was to read it.
Yeah, that is primarily, I mean, I want you guys to introduce the idea that 2 boosts leads to a rotation, but I cannot really ask you guys to do anything on that because it's a little messy. And we are just beginning this whole thing. Staying in one dimension is good.
Yeah, that's the thing that I missed at first is that the questions you're asking are kind of it's a 3-dimensional system.
Yes. Yeah, in one dimension it will be obvious, I suppose. Yeah, exactly. Yeah. Okay. You're still missing Luke. Luke is always. I think he's coming from. What did you say?
Probably so. Biking.
Yeah.
Okay.
Yes, I can never ride my bike to school.
Yeah,
Or if I did bring a bike, it would not be a pedal bike. It would be.
Yeah, for sure.
Yes, I got my acoustic levitator working this morning. I actually had a little free time, so I got it fixed. So it's working now. If you wanted to see it at some point.
That'd be awesome.
Actually, I can show you. I think it's on my table running right now.
Okay.
You can see it, but I don't know how cool it'll be. Where's my screen so I can see? Can you see that?
Yeah.
See the little white,
Yeah,
white balls?
the 4 dots, right?
Yeah, there's, yeah. Uh-huh.
I think I'll
Yeah.
it. Maybe it will get bigger.
Yeah.
Oh yeah, wonderful.
So I got it working this morning.
So what?
It's been through hell and back, basically,
4 dots
but
of
it
styrofoam
survived.
balls,
Yeah.
balls.
Yeah,
And
they're
it's
little styrofoam
floating.
balls.
Okay, very cool.
Yeah. So I could like pluck one out of here.
Cool.
Cool.
Like that.
Nice.
And you can place them at the half nodes.
Uh-huh.
And this is audio, right? And this is sound that is floating, making it float, correct?
Yep, just sound.
Are they very like sub-audible frequencies? Or
Sometimes if you put them in there and you create a disturbance, they'll shoot out like that.
what kind of what frequencies are you using? Or what frequency are you using now?
This is 40 kilohertz,
Okay.
40,000 hertz. You might be able to hear it. I can't actually hear anything here. I'm not sure if you guys can hear something
40
or not. but-
kilohertz? No, right? No one can probably.
No, it's very high.
Yeah, well, but through the computer you can hear it because it'll pick up, pick up sound. So like if I record this on my phone, you'll hear a zzz the whole time when you review the recording.
Okay.
So it actually picks up the sound,
When I
changes
first
the
saw your setup, I
frequency to where you
wondered
can
why
hear
you're
it.
hiring an Instapot.
Yeah, that's what I thought too.
Oh, yeah. This thing's a lifesaver. This is an Instapot and what's the other thing called? Air fryer.
No,
So when you need to make something in a short period of time, it's very nice.
You had
It's
suggested
basically how
that
I
you
eat
might
every meal.
show this or you might describe this at the potpourri seminar. Last semester, you
Yeah, I think I could definitely do that, but I think I would want to put together, the physics behind it a little bit.
think you will be able to tell something?
From my side of it, yeah, I mean, in order to fill an hour, I would need some time to prepare, but it would be something I would be interested in doing.
Next week?
If I like put something together this summer, next week? No, not next week. I can't do it.
You should show
I can't
me.
do it next week. We have an exam next week.
Yeah.
Yeah, I'll show it. I can bring it and then you can show it to people in person if you want. It's fun to play with. I'll bring it tomorrow and you can show people and then maybe I can
But
do
tomorrow there is no potpourri. Today.
No, I'm saying like I can show people today the potpourri. But I'm saying like if you want me to give a presentation, I don't have, I just have like little scratch notes and stuff.
I know.
I built it 2.5 years ago. So I'd have to refresh my memory on.
Yeah,
I mean, I could show it, but.
Yeah, just log in for first 5 minutes.
I'll do it justice.
I think they will like it. I think that's cool.
It's pretty cool.
Yeah.
It's fun. You could do water too. You have a really small.
Oh, you can
like
even a droplet of water.
diabetic needle.
That's very
Yeah.
cool.
Mm-hmm.
Have you done it?
Like I can take water. Yeah, I can take water and add it to those styrofoam balls, and then when the trapping force reaches its maximum, the water will begin to spin around the little styrofoam balls and create like a cylinder kind of water. It's kind of cool.
I was saying without a styrofoam base, for example, if you start with an ice ball and then the ice will melt, will the water stay as it is?
Sure. I mean, you can put it in there as just water itself. You don't have to have
And
ice.
it does
Doesn't have
stay
to.
there. Nice. Yeah.
Yes, it'll stay there. Mhm.
Cool, cool.
It's a lot more unstable though. So you can put like one, maybe two droplets of water. But anytime there's a disturbance, then it'll just shoot. You can see the wave, like all the half nodes across, it'll just shoot the water across. And be like it's kind of cool.
Should get a fast camera and
Yeah, that
fast
would be really cool.
camera and actually put some videos together. It might come out really nice.
We'd probably put them on the.
Yeah, it would be neat.
Yeah,
Yeah, they
exactly.
probably
Yeah.
would.
My original intention with that was right before I came to grad school. I wasn't sure if I was going to come to grad school and do all this, but I wanted to make a multi-axis one. And instead of just the one axis that I have, you can do, make it much larger scale, and you can do multi-axis. And it would be cool because you could write a program essentially in like Arduino that would dictate some frequency. So you could like float wave functions. So you would actually be able to see the wave function with styrofoam balls. So you would just take the styrofoam balls and kind of drop them, or powder, and drop it in between. You would see the actual wave function. It's kind of cool.
Nice. Yeah. But with this itself, if one gets clever, you should be able to do some things, right? Like maybe something new or something. One has to come up with a nice problem.
Yeah, I think I certainly think you could do some cool stuff. I know they've used so for instance, like in Dr. Talapatra's research, they use sonicators. And I think if you found a way to bounce something between the two, like the half nodes or the full wavelength, you could get some pretty, like you could purify some stuff probably that way through sonication. But they do this with lasers, and they do this with magnetic stuff as well. But I think the sound one's cool because it's a pressure wave, so it's a little different. So it has, you can levitate larger things than you could with a laser, obviously. Like a laser you could do.
Isn't this the same as Paul trap in electromagnetism?
Yeah,
How
it's
similar
very
is it?
similar, but
Right.
What's that?
Like
Just for
idea
sound,
wise,
yeah.
yeah. This is of course for sound, yeah. But mathematically probably similar.
Yes, I think so.
Cool.
That's pretty cool.
Is everyone here? 1, 2, 3, 4, 5. No, you're missing someone. Oh, because Jordan is the big one, right? Yeah, right. Always confusing. Yeah. Okay. Oh yeah, I have to see if this works or not, right? Yeah, so homeworks are due homework 6 and 7. Homework 6 and 7 Oh, not 7 is not due, right? So this is not due. It's not due, but Tuesday. And we have a midterm thanks to Moses. Midterm in the class. Right? You didn't get beaten up last time?
Not yet.
Not yet. It's in class. So this will cover, this will cover homeworks 4, 5, 6, 7. So 1 hour exam, 115 minutes exam. Expect elementary stuff, simple stuff. Okay. So go through your home. The best is go through the homework and let's think what can be asked for something that can be answered in 10, 15 minutes. Usually, these are tricky questions often. Whenever you make it short, what I think is very basic might not be the case for students. So, like magnetic moment, for example, and what was. And since we're doing relativity, there's a lot of simple things you can ask in this short answer, something that can be finished in time. If you know what you're doing, something that can be done in 10 minutes, you're done. But if you don't know what you're doing, maybe it takes forever. Yeah, so something like that, I suppose that let's hope it goes well. Otherwise,
Be safe for now.
Yeah.
Okay, so let's finish up this theoretical relativity part, and then we'll go to E&M next class. Not next, yeah, next class on Tuesday. So let's. Yeah, we can say relativistic dynamics maybe now, because no, we don't really, yeah, maybe. I think I can call it, because we talk about force. Like we talk about Newton's law, how Newton's law is like in relativity. That's what we want to talk about. First equation, just a quick review. This is minus c square d square plus. Right, that's our what is it? Differential statement in Lorentz transformation, and then we also have gamma comes out to be equal to c dt over ds. So there is a -1 minus beta square, which is what our gamma bracket on the other side. That plays an important role, or actually better think of it like this: c dt is equal to gamma times ds. So instead of talking in terms of time, talk in terms of invariant time, invariant differential in time, but it comes with gamma. That's the idea. So everywhere you have time derivative with time is velocity derivative with the derivative of velocity with time is acceleration. So instead you want to redo everything in terms of ds, and that's the sort of the goal there. We talked about 4 position. Again, the general theme is that in relativity, you don't try to change too much. It's just that you want to find a 4th physical quantity, like with position, it turns out to be the time. With the velocity, it turns out to be the speed of light. With acceleration, you similarly find the 4th piece in such a way that there is a 4 vector associated with that. So 4 position is ct, and x. Then there is for velocity. Oh, I like alpha. U alpha is c times gamma times velocity times gamma. And always invariant distance is useful. U alpha comes out to be minus c squared. So if you were to measure, so there is no point in comparing velocity or position or time. But if you compare this will come out to be the same in every frame, which in this case is trivial. The speed of light is constant. That's the fundamental point where we started, in a sense. Then we have for momentum. P alpha, which is defined as mass times the for velocity, which of course comes out to be equal to mc gamma mv gamma. And that's good, but the main point is that now you connected. This is the only difference that this is the point where you deviate from Newtonian physics and you define this to be energy, which is not the usual energy, right? There's E over C. There's no gamma that comes up typically. And this you define as momentum. The different momentum, different energy. But again, if you were to, even though this is a new definition of momentum, if you were to measure it in a lab and then compare 5 of you, compare it with each other, it won't match. Right? If you're moving with respect to each other, it won't match. What will match is the invariant quantity associated with it, and that comes out to be equal to minus m squared c squared. So mass that we know is actually the invariant object associated with energy and momentum. Okay, so that's a few things. Then we did for acceleration. So that was for acceleration. That's A alpha was equal to, since it's a second derivative, it gives some extra terms. Remind me, what is this? That's a scalar to begin with. So this is gamma, beta, now gamma is 4, beta dotted with A. Remember, beta is V over C. I wrote it as V over C. So this is beta dotted with A, so that comes out as the same dimension, right? Acceleration and acceleration. And then there was the acceleration itself. So acceleration multiplied by anyone can open gamma squared. So there's a piece that is proportional to the direction of acceleration and another piece that is in the direction of velocity. Remember, beta is having the direction of velocity. So it's beta dotted with A. And I think gamma 4 again. Check. That was your acceleration. Okay. So clear. Notice that this, if you think of the spatial components of acceleration, this has a direction contribution from the velocity and from the acceleration. And that's your standard acceleration, Newtonian acceleration. We also showed that U is a time-like vector. If this is a time-like vector, there was an implication that acceleration was a space-like vector. We can say, let's I have the idea of instantaneous rest frame. Instantaneous, is this correct spelling? Instantaneous rest frame. Like, of course, if you sit on a particle, you're always at rest. But by instantaneous rest frame, what I mean is that Lorentz transformation has to do with a particular frame with a particular velocity. So if I'm moving with constant velocity, there is one frame in Lorentz transformation that connects with me. But if I change my velocity, even though I'm still at rest, but I have gone into another Lorentz frame. Right? If I classify all possible velocity as a set of possible Lorentz frames, if I change my velocity, I have jumped from one Lorentz frame to the other Lorentz frame. Right? So instantaneously, I have a Lorentz frame associated with me. Right? Whatever is my velocity, that particular element in that frame. If I'm accelerating, I have to keep jumping continuously. I have to keep jumping my Lorentz frame because at each time I have a different velocity. Is that clear? So that's what I mean by instantaneous rest frame. So even though a particle is accelerating, you're of course at rest at each instant, but your Lorentz frame is changing. So in that sense, so in that instantaneous Lorentz frame, I have surely beta equal to 0. So this is going to be called, so let's say A alpha. So I'm in that particular, in the instantaneous, why not call it IRF? IRF, instantaneous. That's equal to, I have beta equal to 0, so that's gone. And gamma, because beta is 0, is 1. So this is just having acceleration. But it's not the same acceleration because I'm in a different frame. So let me call that A naught. So I just use this, set beta equal to 0 and gamma equal to 1. And since I'm in a different frame, I don't want to call it the same acceleration. I called it A naught. So that's your A naught. That's it. Okay. So A alpha. So A alpha in any frame. And remember, this is an invariant object. This will be same in every frame. That will be equal to A alpha in the instantaneous rest frame, which is equal to A naught square, A naught dotted with A naught. So the magnitude of this quantity, we will call this the proper acceleration, because this is the same in every frame. The magnitude of this acceleration, when you square root that, that's called the proper acceleration. And we will talk about at the end of the lecture, a particle moving with, like we have in Newtonian physics, we talk about a particle moving with uniform acceleration. It has a parabolic trajectory. We'll talk about a particle going with proper acceleration. What is its trajectory? Is it a parabola or not? That's something that we will investigate. But that's the definition of proper acceleration. Any questions? Okay, that should be good. Okay.
I'm sorry, I didn't actually quite follow why we had 0 as the first component of the instantaneous rest frame.
Because beta is 0.
Okay.
Because you're at rest, right?
Mhm.
It is at rest. Rest frame means beta is 0. Nothing
Yeah.
special about it. Why I add the word instantaneous is that if you can ask the question, if you're in a rest frame, this gets a little subtle. If I'm in my own frame, am I accelerating?
Hmm.
In my frame, am I accelerating?
Mhm.
Right? Because I'm at rest, right? But then the point here is that you're comparing, you always have to associate yourself with
I
some
see.
Lorentz frame,
Yeah.
which is keeping on changing.
Yeah.
So that's what I mean by instantaneous rest.
Yeah, yeah, no, I get that, yeah.
Because otherwise there is this confusion that comes that, okay, if you're at rest, what do you mean by acceleration? Why are we talking about acceleration then?
Uh-huh.
Like in your own rest frame, it is slightly tricky to ask what is your acceleration when you're at rest. In that frame, you're at rest.
Right,
But then we are saying we want to compare with Lorentz frame.
right.
In that sense, you have an acceleration.
Mhm.
Right? Since you're jumping from one frame to the other, there is an acceleration.
Right. And so when we say beta is always 0 in that case, like our velocity with respect to the Lorentz frame?
Yes. So you're once you jump, so stick to one frame,
Okay.
right? In that frame,
Oh,
since you're at rest, that
Yeah.
is 0.
Okay.
The moment you change your velocity, yes, you compensated for the acceleration there,
Mhm.
but then again you're at rest.
yeah, okay.
Right? Instantaneously, you're not rest in the previous moment.
Okay, yeah, no, I follow that, yeah.
So yeah, that is a subtle, or more than subtle, I think, a very, you tend to doubt it. What does that mean?
Mhm.
And it plays an important role, it turns out, or it is.
So I have a quick question.
Yes.
So as long as you're not accelerating, so say you're a particle, then you're not radiating. Even so in your rest frame, say you have some constant velocity, you don't radiate only whenever you change your like speed up or speed down or just speed up.
Mm-hmm. Yeah.
So okay, I think I understand it then. I think I answered
I mean,
my
by
own
end
question.
of the lecture, we'll talk about, like, here is the point, right? I think if I draw a graph, right? So this is your space-time diagram, right? So let's say this is Z and this is C times T. And remember your cone is here, right? Let's think of a trajectory of this kind. That's a allowed world line. Okay. Now remember, if it was a straight line, you're going with constant velocity. So at each point here, so draw a tangent. So let's say this is a tangent. That's an instantaneous rest frame. The moment you go to the next one here, you've changed your velocity, right? You're going faster. So it's not the same frame. You have moved your frame. You changed the Lorentz frame you're speaking with if you're at rest. In that sense, you're changing frame. But if you're at rest, you're always at like at each point of time you're at rest, but they are in a different frames if you want. You're comparing yourself with different people. Or yeah, I think different people gives me this idea. Yeah. So let's say. So let me highlight this better. So that's your curve. This is. So there are people standing and watching, let's say. This is one person. That's a frame, right? That's a Lorentz frame. That's another Lorentz frame. Is that clear what I mean by 1, 2 Lorentz frame? Because they are going with constant velocity. So this is a person who says that, okay, anyone who is rest with respect to me, they belong to my set. Right? This is another set of people who are all at rest with each other. If you're accelerating at an instant, you're at rest with respect to one, and at next instant, you're at rest with respect to another person. So if you want to compare your quantities, this 1 and 2 have to talk to each other. You cannot talk with yourself because you have changed frame. So between two instances, since you changed frame, you have to discuss with another frame, and that's what I mean by instantaneous response. Was that helpful?
Yeah, actually it was. Yeah.
Okay. So with that, let me proceed. So that we are going to keep on talking about proper acceleration. So there exists a proper acceleration when the acceleration exists. But then you can talk about a particle that is going with the same acceleration all the time, same proper acceleration all the time. You can change its components, but it keeps its proper acceleration, same magnitude. So that's what we will talk about. But let's do a little more on proper acceleration. So this is A naught, right, squared. That's the same as A alpha. Let's calculate that. So take your forward velocity and the time component, you square it and put a negative sign in front of it. So that's equal to minus gamma raised to 8, beta dotted with A square, and plus, so there's a lot of, so there's a whole square term there, right? So there's a vector A square dot vector A square is the same as A dotted with A, that's the same here. So that's gamma 4. And then there is beta square plus beta dotted with beta will be beta square. Beta dotted with A square. And then gamma 8. And then you have plus 2 times beta dotted with A the whole square. Right, cross term here, and there's a gamma 6. This simplifies. Let's begin by collecting these two. So this is minus beta dotted with A the whole square, gamma 8, 1 minus beta square. These two I collected together. But then remember, gamma square times 1 minus beta square is 1. So we have a simplification due to that a lot. 1 minus beta square is equal to 1. So that becomes gamma raised to 6. Whatever is remaining is plus 2 times beta dotted with A. Oh, so I can actually put that also in, right? So do it next time. So gamma 6 plus A, let me write this as A dotted with A gamma raised to 4. This is gamma 6. This is beta dotted with A square gamma 6 plus 2 times beta dotted with A square gamma 6 plus A 4. And again, there's a cancellation there. So we have beta we'll talk about this in a minute, but let me manipulate this a little bit so that there is a nice comparison we can have. So I look for an identity. So remember, if I were to do beta crossed with A and then square it, right, which is basically dotting it, right? So if I were to square this, that's a scalar, right? That's the same as, so if you use your identity, so that is the same as beta dotted with beta, which is beta square, and A square, A dotted with A if you want, so A square minus of beta dotted with A square. Oh, we need a quiz, right? So
What happened to the negatives? What happened to the negative sign? I guess that what you're trying to
There is
explain.
-1 and there's a 2 there, right? These were the same.
Oh, okay. Yeah. Okay, yeah.
Prove this identity. Okay. So small quiz, you can use this index notation. Sorry, a few steps it comes out. Let me use that in the earlier result. And I get, let me write that as vector A square gamma 4 plus beta dotted with A is beta square vector A square, and then there is gamma raised to 6 minus beta crossed with A square gamma raised to 6. Something went wrong. Let's prove this here. Okay. Check this. So beta crossed with A, dotted with beta crossed with A is epsilon I j k beta j a k and epsilon I m n beta m a n. So that's delta j m delta k n minus delta j n delta k m and beta j. Yeah, so that seems to be okay. What's going on? Okay, it's correct. So, can I do this part? Did I lose the sign here? Is it minus by any chance? Okay, why am I concerned? Okay, plus A dot square beta dotted with A, I put it there. Beta square A square minus. But this doesn't collapse, right? Cool. Plus. Let's see what happens. Yeah, let's. Okay. So this all seems okay. That's gamma 4, and then there is gamma 4 plus beta square. Oh, yeah, that is system. Oh, no, this is all okay. This beta square gamma 6 minus beta crossed with the gamma 6. Right, that should be fine. What is gamma raised to 4 plus beta square plus gamma square? So that is gamma 4 plus beta square gamma 6, right? So that's the same as gamma 4, 1 plus beta square over 1 minus beta square. Right? which is the same as 1 minus beta square plus beta square. The beta square cancels out. So that's gamma 4, 1 over 1 minus beta square, which is gamma raised to 6. Correct? So this is the same as 6 minus beta crossed with A square gamma 6. Okay. With me? So can I raise this? So we have got two expressions for the magnitude of proper acceleration. Yeah, we've got two expressions. One is this, and the second was, let me write this down here. Second was, yeah, these two, right? I think right there. So it's gamma raised to 4 plus beta dotted with A square and gamma 6. Agreed? Let's consider the scenario when velocity is parallel to acceleration. That happens when something is moving in a straight line. Think of an electric, a charge beginning from rest in an electric field. Electric field, maybe. Okay, but it has to start from rest, so that's important. In that case, beta dotted with A is 0. No, beta crossed with A is 0. Right. And then you go to the first expression and you say that, oh, then the magnitude of acceleration, this is what we mean by how does the acceleration, does it dilate, does it contract, or so on. It not only dilates, but it dilates by a factor of gamma cube. Time dilates by a factor of gamma. So acceleration has this distance over time. So probably you can argue that each one of them gives you a gamma factor, and there is a gamma cube that comes in. So acceleration in the rest frame is whenever you're moving no, it is contracting, right? Oh, I should actually, sorry. I think let me interpret this correctly. So acceleration in a moving frame is actually equal to acceleration in the rest frame over gamma cube, right? So it is contracting. So acceleration contracts by a factor of gamma cube. So that's the factor. It's not that. But the important point is that there is a factor of gamma cube there. But now let's take another situation where velocity is perpendicular to acceleration, and the classic example is magnetic field. So magnetic field, in that case, beta dotted with A is 0. And then you go to the next expression there, that's different. So it still contracts, but only by a factor of 2. Right? So fundamental or very, if you were to make measurements, it will look very different. So it will come out very clearly. Okay. Okay. So that's, we'll come back to this acceleration very quickly. But now that we have acceleration, so we have position, velocity, acceleration, force, right? For force. Very straightforward. F alpha will be just m alpha, or we'll define this as m times. So we have two options now, right? We can either think of it as just mass times acceleration, which is for acceleration, or I can also start from momentum and take the derivative with respect to the s and then multiply it with by c, right? That's also perfectly fine. Okay. So that gives two different expressions. So let me start with the second equality. The force is equal to momentum there is c times dt over ds and dp alpha over dt. That's your gamma. That's a factor of gamma. And this one is energy and momentum, right? So it is d by dt of E over c. And the spatial components are dp by dt, the relativistic momentum and relativistic energy. Or if you want, right? So I can say, oh, that gamma is there. So yeah, this is okay. So this is gamma, and explicitly, this is change in energy with time and change in momentum with time. We will define our three force will be defined as change in momentum over time. It's the same idea as Newtonian, but now this is different. This is definition. It is different because P is different. You do not change the equation, but since we changed our definition of momentum, there was a gamma in there. So in principle, this is no more the Newtonian equation. Right? P here, recall, so this is the definition, so recall, P is now mv gamma. Right? So in that sense, your Newton's law has changed, but very slightly. If you accommodate for that, you're good, right? That's your Newton's law, and from this point you know everything, right? Then you keep doing whichever system you want to work with. But let's figure out a little things here. What is the fourth component of force, right? This is your force with this gamma. What is the fourth component in there? That's interesting. What is that? And that's the rate of change of energy with time. That's power, right? So power is the fourth component of force. But let's look at, is there a nice way of looking at it? Remember that in Newtonian physics, dE by dt can be thought of as, if you don't think of it as an equation of the work done by a charge, then this is F dotted with d over time. So this can be thought of as F dotted with v in Newtonian physics. Force dotted with velocity is rate of change of energy, which is of power. And you again ask, oh, is this going to stay the same? This is the Newtonian physics, it works. But is this going to remain the same? We're not sure, so we have to check it out, right? Let's see if that works or not. And it will turn out that it remarkably, even with the changed definition, it will work exactly. So this will, so whenever you're doing relativistic physics, that's one equation you want to keep in mind for Newton's law. And the second is, right here, because A alpha times U alpha, what is that equal to? Because they're perpendicular, right? That's 0. Right? That is 0. And because of that reason, F alpha times U alpha will also be equal to 0. And F alpha we know is, so what does this mean? So let me write this. F alpha is gamma over C dE by dt, and gamma times dP by dt. That's F alpha. And U alpha, remember, is C times gamma, B times gamma. So our condition that F alpha U alpha is equal to 0 will be multiply these two, so that's gamma squared dB by dt with a negative sign because of the Lorentz scalar product, and plus gamma squared V dotted with dP by dt dotted with V. But that's equal to 0. That should immediately implies gamma square cancels out. This is force, so dE by dt is equal to F dotted with V. This stays intact. And in Einsteinian physics, except that now the definition of energy is the relativistic energy, and here definition of momentum, the relativistic momentum inside the force. Those two are the equations you want to use whenever you're working with in relativistic physics.
So really quick, so does this mean that the Lorentz force equation just would remain the same? So you would
Yes,
just
Lorentz force equation. Remember,
charge?
remember Maxwell's
So
equation. Remember Maxwell equation is the bed where, what is it called? Is where relativity came from, right? You respected Maxwell's equation and gave up Newtonian physics. So everything stays in Maxwell's equation. It is the Newtonian physics that changes. So Lorentz equation is going to be invariant. Like that will stay as it is, and we'll talk about it a little in the next class in the relativistic notation.
Okay.
Sounds good?
Except it would be so the force would be the change in the momentum with respect to the position, right?
Yes.
So,
yes. Yep. So F is equal to, so your point is F is equal to Q times E plus Q times V cross B. Right. So this force now is this dP by dt. So is that your question?
yeah, but I was just thinking that it would be with respect to the position. So the change in the momentum, like change in P alpha. So the force would be change in P alpha by the change in position. Is that wrong?
P alpha?
Don't worry about it.
You mean P alpha here? No, this is P.
F alpha. So the force raised to alpha, you know?
No. This is the 3 force, remember. This is the 3 force.
Oh,
This is the 4 force.
okay.
Are you able to see what I'm pointing?
Now I'm unconfused. That fixes it. Okay.
Yeah, 4 force should not be confused with 3 force, right? 4 force is just a for bookkeeping purposes, just to make sure that you don't compare things with different observers. Like it is meaningless to compare what you measured for force and what I measured for force, because they are not invariant concepts. So you need to construct a 4 force and then find the magnitude. That's what you have to compare with. But 3 force still needs a definition. So this is the definition of 3 force. Does that help?
Yeah, that answered my question. Yeah.
Okay. Okay. So we need to do an example, correct? Now that we have force equations, we should do an example. And this is called a particle going with, this is called hyperbolic acceleration, let's say. A particle moving with hyperbolic acceleration or proper acceleration, or I like to call it Rindler acceleration, or proper acceleration. The most popular is proper acceleration. You want to look for proper acceleration. And in a straight line. Okay. So we are assuming that v is parallel to acceleration, and which means that a naught, so there exists a constant, and everything is one dimensional, right? So once if you're in parallel, velocity is parallel to acceleration, choose that to be your axis. So no more vectors, right? Everything is just, it has a sign, positive and negative, but everything is one dimensional. So I don't have to write the magnitude now anymore. So there's an acceleration which is equal to acceleration times gamma q. That's coming from our discussion of proper acceleration. Let's divide by the acceleration here is dv by dt. So I have our equations of motion are dv by dt times gamma q is equal to a naught. Let me divide by c and let me write it as beta. That's fine. If you want, how do we do parabolic trajectory? You will begin with saying that acceleration is equal to g, right? Which you would say is dv by dt, correct? And then you will integrate and get v is equal to g times t plus v naught, and then do another integral and get parabolic trajectory, right? That's how you would proceed. You want to do the same thing with this. Right? Here now the equations have changed, right? And ask what is the trajectory that corresponds to this. For that, there is a nice little identity we should look for. Let's look for what is time derivative of beta times gamma. So that's d beta over dt times gamma plus beta times time derivative of 1 minus beta squared. That's the same as d beta over dt times gamma plus beta times, that is minus 1 by 2 when I take a derivative, and then this becomes 1 minus beta squared or gamma cube, right? 2 by 2 and minus 2 beta. So all that together, we have, and eventually d beta by dt. The chain rule have eventually meant d beta by dt. So that's the same as d beta by dt. I can pull out a gamma from there, so that's gamma, and that is 1 plus beta squared over 1 minus beta squared. Which we already saw that coming it was coming earlier. And that's nothing but gamma squared, so that's gamma cube beta by dt. That's nice because that's our equation there. So instead of this, I can write total derivative of beta times gamma. So my equation of motion for a particle moving with proper acceleration is this. That's easy because now I can integrate this with time. Any questions? Stage? Okay. Integrate with time, this immediately gives me beta times gamma at some time t minus beta times gamma. This is the integral constant of integration if you want. That's equal to A naught over C times T. That's how you will integrate. Move the camera. Let the particle shot from rest. Okay. At time t equal to 0, at t equal to 0, beta is equal to 0. That's my initial condition, if you want. And that sets this to 0. So simplification. So my equation becomes beta times gamma is equal to A naught over C times T. That's the same as beta square over 1 minus beta square is equal to A naught over C square times CT. Let me solve for beta here. So I put this on the, let's write it once. So beta square is equal to A naught over C. Oh, this is C square T. Oh, I messed up, right? Sorry. So sorry. So this is T square, and let's say C square T square. C square CT square. Just collecting it in such a way that this is dimension. This is a dimensionless quantity now. And is it dimensionless quantity now? No. This is having the inverse, this is having the distance in here. So that's distance 1 over distance if you want. Okay, so this is equal to beta square times square C square T square minus beta square times A naught square over C square. Pull this on the other side and solve for beta, and I get beta is equal to, that involves a square root. So it's A naught over C square times CT divided by 1 plus that's what it is. Okay.
Did something happen, or is it just me?
I haven't heard anything he said in the last couple minutes or so.
Yeah,
Yes. No.
maybe he disconnected.
Mm.
Oh yeah, he's not on air anymore. He's
So
probably still talking.
yeah. He's, I think it said Aaliyah's the new host now.
Oh. Oh. Well, you have to teach us then. Go ahead and finish this. Yeah.
Right? Yeah.
Excuse me, Luke and Michael, I have a question.
It's not that bad.
Does Dr. Bird mention anything about the deadline for the last homework?
No, I'm not turning the
No, I don't think he's ever set a due date. But Luke, Ken, and I were talking yesterday about maybe turning it in on Friday. But yeah, we're thinking about just kind of setting our own due date and turning it in on Friday sometime. But I'm not sure if I'm going to be able to turn it in tomorrow. So I might turn it in Monday.
Thank you.
Yeah.
Yeah, we expect him to sort of remember about the homework today, and then we'll see where where that gets us. But yeah, I think Monday
Okay.
probably, but I'll try to do it as soon as possible. Yeah.
Okay, I'll bill it on you guys. This is on. Okay, let me try to finish quickly. Okay, are you guys there? No.
Yes.
Yep,
Yeah.
we're here.
Yes.
Yeah.
Okay. Great. I think it is not our university wireless. It has to do with something to do with the computer. But let me quickly get this finished. Okay. So let's integrate on both sides. So we will get V over C at some time minus V over C at time t equal to, no, this is position, sorry, not position. This is position, right? Yeah, so x as a function of time over C minus x as a at time t equal to 0. Let's put that as a constant. Why not? Plus constant is equal to, I'm not calling it C so that there is no confusion with C. That's integral dt a naught over C squared times CT. Okay, can I check this? So that's okay, distance, right? 1 over distance, time, yeah, that's dimension 1. Okay. Let's substitute 1 plus whatever is in the denominator to be some s or p, 1 plus a naught over c square p square is equal to y, let's say, right? Then a naught square c square 2 times t is equal to dy dt. So that's the same as there's only one a naught over c there. So a naught square over c square times c times t is equal to dy over, there's another c there, and 2 times a naught square over c square. Just collecting the c's. Okay, so and this is dt. So this is dy. So this is 1 over c 2 times a naught, so c square over a naught, and this is dy over y, square root of y. So that's a distance as a factor of half. Why is the factor about that? So c cancels out. So we have x as a function of time plus constant is equal to c square over a naught, factor of half. What is the integral of this? Y raised to minus half plus 1 over half, right? Oh, that's the half that cancels out. So that's square root of y. but y is there. So this integral is 1 plus a naught. That's a solution. It went a little quick so that we can finish this quickly. That's your position. So what does this mean? I still have a constant. So remember, I can put an initial condition. So this is a special initial condition just for convenience or simplicity in the equations. Let me choose, right, at t equal to 0. At t equal to 0, this goes away. So let me say that x at t equal to 0 actually is c square over a naught. That's a very special choice. But if I choose that, then this constant, this implies that this constant is equal to 0 under this special choice. So my solution becomes c square over a naught square root of 1 plus. Square this out. If I square it and bring this to the left, I get x squared, x as a function of square minus, so when I square this, this exactly cancels out that, so minus c squared e squared is equal to c squared over a naught, that's a distance squared. That's the equation of a particle going with constant or proper, a constant proper acceleration. This is a hyperbola. Which looks the following way. So if I were to plot this, that's your x, that's your ct. X at time t equal to 0, that's your c square over a naught. That's your c square over a naught. So that's x at time t equal to 0. I choose that to start from there, and it goes like this. I can do one small thing. Let me consider a scenario where a naught over c square times c square t square, right? That's that quantity inside the square root, is very much less than 1. Then I can actually series expand on that, which means to say that I'm talking about time very much less than this. One of the c square cancels out, so this is a naught over c, so t is c over a naught. So under times, which means that for small time, when the particle begins, don't go too far. If you're very close to the point where you began, then x as a function of time can be approximated as a naught times the series expansion of that is 1 over 2 times a naught over c square squared times c square t square. This was x at time t equal to 0. And the second term is all the c square nicely cancel out. And this gives you half a naught t square. Right? That's your non-relativistic acceleration. So that's down here. Right? That shows. So this is non-relativistic. And I'll stop there. Thank you. Any comments, questions? I hurried up in the end, hopefully. It's not that bad.
Noticed you made a small error in the,
Oh.
in the substitution, the back in the substitution, just with the,
But then since I knew the answer, I fixed it. Huh?
up on the right, yeah, the squared there shouldn't be a naught doesn't be squared.
Oh, here.
Yeah, here and above as well.
Yeah, good.
Most people probably caught that as well.
So Moses points out that there was a square here. I just erased it. Whiteboard, you can just erase it on your notebook here to complete. Okay, thank you. So with this much of review of relativity, next time we will write down Maxwell's equation in this language. We want to, for every physical quantity, we want to have this fourth quantity, right? If it's a vector, we want to associate a fourth piece there as much as we can. Oh, and I should kill it so that I'm using data.
Okay, bye-bye.
Yeah. Thank you guys. Yeah.
See you later.
So